right? If you take the pressure to be 10 to the minus 6 torr, you put it in here, then what do you get? If you have a pressure 1 to 10 to the minus 6 torr, it means that you would have one monolayer in 1 second's time, right? Because if you substitute in here, the surface density is just 10 to the 6 times P, so then you would get one monolayer per second. So the Langmuir unit is very nice because the Langmuir unit essentially tell you if 1 Langmuir means that you have one monolayer per second, essentially, right? If your pressure is appropriate, you can get one monolayer per second. So, so this, further to this, Langmuir unit, right, which is related to this simple calculation that we have, is that the time of coverage, how much time you got to cover the material, right? And to cover the material is a somewhat complicated thing, because if you put some gas onto some surface, right, it depends on how sticky the gas is, right? So you put a bunch of gas, hit a bunch of gas onto this surface. Some of it may stick, some of it will not stick. And the fraction, the amount of the gas particle that stick, you calculate this relative fraction. This fraction is called sticking coefficient. Okay, so if you can imagine if you cool your material down totally, very low temperature, you can imagine you throw every molecule to this cold surface, everything you get stuck, right? Because that's what we anticipate. So if you're at a low temperature, your sticking coefficient will be 1, right? Because it means that 100% stick, right? You throw stuff at it, it will all stick. And so people think about, okay, it depends on how sticky this is, and it is expressed in terms of this called sticking coefficient, as here, sticking coefficient, as here, which is this is the probability of a incoming impinging particle become adsorbed or thus stick to the surface. So that's formal definition. And you can define something called the amount of time of coverage, how much time that the molecule hang around on this surface. And it turns out the amount of time, sort of resident time on the surface, is 1 over the flux that we calculate, the flux here, times the sticking coefficient. So it's 1 over n times s. Okay. So if you clean your surface right away, right, in some extremely good racket, totally clean, then usually it means that the sticking coefficient at that point is 1, because there's nothing absorbed on it. So anything you throw out, it will get stuck, right? So, but then if your surface gets dirtier and dirtier, or you throw stuff at it, not all of them will get stuck. So that means that your surface, in fact, the sticking coefficient depends on how dirty your surface is already. So it depends on the coverage. So that's another way of saying it. So the surface, this sticking coefficient is coverage dependent. So when it's clean, that means coverage is 0. Sticking coefficient should be close to unity for all material. As the surface gets dirtier and dirtier, the coverage becomes higher and higher. Sticking coefficient will become longer, smaller and smaller. And if you have a smaller number here, what does it mean? It means that you lengthen the resident time, the time of coverage that you have. Okay. So in the end, what you got is that if you look at this resident time, right? You want roughly about an hour of working time for your experiment to measure something, because you need to time the number, you need to make measurement, and it does take some time. So let's say 1 hour, and you work out this number. You assume sticking coefficient of 1 because you assume that your surface is very clean to begin with. So you put 1 in here, and then you try to work out if you need an hour for this resident time, how much pressure do you need? And you do this calculation, it turns out to be 10 to the minus 10 torr. You need at least 10 to the minus 9 torr, which give you about 1,000 seconds, right? 10 to the minus 10 torr is 10,000 seconds, which is over and close to 2 hours, right? So this 10 to the minus 10 torr is known as ultra-high vacuum, right? So you at least have over 1,000 seconds to work on your experiment to make this measurement before your surface gets dirty again, you know. So that's why people call ultra-high, because it's high vacuum by convention, 10 to the minus 6 torr, and it's much lower than 10 to the minus 6, so you get ultra-high. And because of this, so getting 10 to the minus 6, 10 to the minus 10 torr require new technology, and people require all this nice stainless steel chamber, and how do you seal, prevent air from getting into the chamber, how do you make the chamber leak tight. So a whole school of vacuum technology need to be invented to deal with this 10 to the minus 10 torr situation. And people have done that. So these are standard technique in terms of 10 to the minus 10 torr. Okay? So in order to study this clean surface and not dirty surface, we must therefore, so the punchline here is that we must, in order to do this, we must maintain an ultra vacuum situation in order to maintain, to have sufficient time to allow us to make the measurement. Okay, and you may say that, well, you know, even if you have 10,000 seconds, that doesn't seem to be sufficient. You may need longer. So I just point out here in the notes here that because your resonance time is depending on the sticking coefficient, right? Here is 1 over 10 to the 6 p times the sticking coefficient. So really, if the sticking coefficient is coverage dependent, so once you have a little bit of dirt on it, or the particle that you want on it, your sticking coefficient actually will change, will become smaller, and if your sticking coefficient becomes smaller, then the amount of time you have will become longer. So in fact, your sticking coefficient is a complicated number. It's a function of the coverage. It depends on the condition or the coverage of the surface itself. It is not a simple number. It's not a constant either. So as you change as the coverage change, the sticking coefficient will also change, and therefore you may have longer and longer time. So even though you may have you may say I only have in 10 to the minus 10 torr, I only have 10,000 seconds. But the actual working time is longer because once you get coverage on it, the sticking coefficient has changed. Okay, so the actual working time for experiment 10 to the minus 8 is actually a lot longer than what we have the simple relation, because the S here depends on the coverage that you have. Now, this created a problem because of the requirement of the technique, right? That we are dealing most of the time. The technique we look at the surface involve charged particle beams, and that in turn involve vacuum, not just vacuum but ultra vacuum. So this creates a problem. So what you study is not in its natural state, right? So if you want to study catalysts, usually catalysts are pressurized material. So you put catalyst in a pressurized chamber. So that's not really vacuum. And so there was various questions about this surface science usefulness of surface science because of this so-called pressure gap problem, right? So how can you trust? So the question is that, can you really trust that something you learn, that information you get from the ultra-high vacuum condition, and apply it in real-life condition, like in catalyst, you know, and above atmosphere type condition. So there has been some question about this, but I think the answer to this is that, well, certainly you cannot study the kinetics of these because the reaction kinetic does depends on the pressure. So if your pressure is high, your kinetic will change dramatically. But you may be able to determine what happened at the instant your reaction takes place, at the early stage of the reaction. So even for catalyst, right? Because when you have a catalyst, in the first instant, the catalyst meet the reactants. You may be able to study in ultra-high vacuum condition because that should represent the early stage of the reaction, the